In this lecture, the following are discussed: sharp and diffuse transformation interfaces, phase diagram and free energy diagram of spinodal decomposition, spinodal decomposition proper, and comparison between phase changes by spinodal decomposition with that produced by nucleation growth type of transformation. Spinodal decomposition is a continuous phase transformation which occurs over extended spatial scale, in which local composition fluctuations are amplified with time. Spontaneous modulated compositional variations are formed over the entire matrix space and temporally amplified until the final microstructure containing a finely disseminated equilibrium phase mixture is obtained. Typical spinodal transformation occurs very rapidly because a finely disseminated phase mixture is the end result of spinodal decomposition. The mechanical properties are improved as a consequence of transformation. Now, sharp and diffuse interfaces. In the region surrounding X0 in figure B, a schematic of a variation of a composition variable C or capital X is shown. The variation around surrounding X0, the variation is typically a curve and it is extended. This curvature is extended over certain length. So in contrast with this, if you consider a sharp interface, so in this short interface between two phases, alpha and beta, of a different chemical composition, so the composition variable extends right up to the interface, and ideally the interface thickness is 0, and there is a discontinuity in the composition variable at the interface. So on one side you have got the composition corresponding to beta phase, and on the other side you have got composition which corresponds to alpha phase. So it is assumed that here that alpha phase is homogeneous, like so is also beta phase. So there is a discontinuity in the composition at the interface, and the interface thickness is assumed to be 0 here, ideally. In the case of in the case of diffuse interface, it has got a finite width. Interface has got a finite width across which there is a variation in the composition. So the relation, now let us compare these two. The sharp interface, in nucleation and other type of transformations, phases are separated by sharp interfaces with abrupt change in chemical composition. In continuous transformations, the two phases are separated by interfaces with a smooth change in composition. Composition changes from that of the one phase to that of another over the length scale, which is finite. Ideally, a sharp interface has got a 0 thickness. Diffuse interfaces has got a finite thickness. The sharp interfaces can be classified as a glycine or non-glycine. Among the non-glycine interfaces are coherent interfaces, semi-coherent interfaces, or incoherent interfaces. The interfacial energy of these depends on the structure. The interfacial energy of a diffuse interface is the result of computational fluctuations over a short wavelength when the concentration profile exhibits intense gradient and curvature. The interfacial energy has a direct influence on energy barrier of nucleation and growth type of kinetics and on the morphology of new phase. In the case of diffuse interface, the free energy of the interface has contributions from the chemical, gradient and coherent energy contributions. Phase and free energy diagrams of spinodal decomposition. Spinodal decomposition can be illustrated on a phase diagram exhibiting a miscibility gap. Phase separation occurs whenever a material transitions into the unstable region of the phase diagram. The boundary of the unstable region, sometimes referred as the binodal or coexistence curve, is found by performing a common tangent construction of the free energy diagram. So in this diagram, alpha phase is stable everywhere outside this inverted dome type of phase phi, where alpha is no longer stable, and it may separate into two phases, alpha 1 and alpha 2. So the boundaries which separates this immiscibility region, immiscibility means a single phase is not stable and it is separated into two phases. So this miscibility gap is defined by this interface, this curve, and this curve is called as a binodal or coexistence curve. It is called as coexistence curve because two phases, alpha 1 and alpha 2, are stable inside. Inside the binodal or miscibility gap is a region called the spinodal, which is found by determining where the curvature of the free energy curve is negative. Binodal and spinodal meet at the critical point, which is this point here. It is when a material is moved into the spinodal region of the phase diagram that spinodal decomposition can occur. If an alloy with a composition X0 is solution treated at high temperatures T1, that is X0, this is the X0 alloy and it is here, solution treated here, and its structure is alpha, and then rapidly cooled to a lower temperature T2 here. So it is you bring it here by quenching or rapid cooling. The composition will initially be same everywhere and its free energy will be G0 on the, so corresponding to that you have got G0 is the energy on the Gibbs free energy curve. However, the alloy will be immediately unstable because small fluctuations compositions are amplified so that A-rich and B-rich regions are reduced. So such a separation of alpha into A-rich and B-rich regions leads to lowering of the free energy. This transformation is thus associated with uphill diffusion, so which takes place until the the equilibrium two-phase mixture of compositions x1 and x2, not x1, x2, corresponding to this and corresponding to this. So corresponding to these 2 points is obtained. Spinodal decomposition occurs in materials systems exhibiting a miscibility gap. Miscibility gap is an area within the coexistence curve in equilibrium phase diagrams. Coexistence or binodal curve is a bell-like curve in a binary phase diagram, defining the temperature and composition where single phase is either metastable or unstable. Spinodal curve separates a metastable region from an unstable region in the coexistence region of the binary phase diagram. So the material is unstable here in this portion and in this portion, and it is spinodal decomposition occurs here. So the phase alpha, which is metastable in this domain, in these domains, can disintegrate into two-phase structures by a nucleation network type of transformation. Figure A shows the miscibility gap defined by the bell type curve. Again you have, which is obtained by applying the common tangent construction. So how do you obtain that common tangent construction? So you have called the alpha is equal to this temperature here. So corresponding to that, this is the free energy of alpha, which is greater than that of the two phases alpha 1 and alpha 2. We can say that I have got this is alpha 1 and this is alpha 2. So consequently, the mixture of this alpha and alpha 2 has got a lower free energy than G0. So consequently, the alpha is unstable here. So it will undergo a decomposition. So any homogeneous solution alpha cooled from T1 into the miscibility gap at T2 will tend to decompose into A-rich and B-rich regions with a net reduction in the free energy. The chemical spinodal curve is defined by the locus of the points S1 and S2 corresponding to inflection points in G versus X curve. So this is X is here and this is the gives free energy. These are the two inflection points corresponding to a temperature T2. If you vary the temperature and then obtain these composition limits of these two phases and plot such a locus of such points, then we end up having the spinodal curve. If a homogeneous solution is cooled into the region between the chemical spinodal and miscibility gap, that is here, then large compositional fluctuations are needed before phase transformation can occur. This happens by a process known as nucleation growth. So if fluctuations are small, then they are dampened. So consequently, the alpha will stay in the metastable condition. If given sufficiently high driving force, external driving force, then it will the alpha will disintegrate into two phases by a nucleation growth process. Spinodal decomposition can occur for any alloy whose free energy curve has a negative curvature, that is d2g dx2 should be less than 0. Alloys must lie between the 2 points of inflection on the free energy curve. The locus of the points on the phase diagram is known as the chemical spinodal. Phase decomposition to phase mixture by nucleation growth. if the alloy lies outside the spinodal, small variations in composition, say for example you have called this alpha of this composition x0 prime from temperature T1 to T2, small variations composition leads to an increase in the free energy because corresponding to that, so this is the free energy of as pinched alpha, and the mixture of phases alpha 1 and alpha 2, they have, the mixture has got a free energy which is lies above this point in this along the energy axis. So consequently, so such a fluctuation, composition fluctuation is unstable, so consequently the system reverts back to equilibrium. So consequently here, for small fluctuations, there will not be a transformation of alpha. But if there is a large fluctuation such as by nucleation growth, then alpha can transform into the product phases. So normal downhill diffusion occurs in this particular case. Here the diffusion is uphill. The alloy is metastable if its composition falls in the region between the binodal and chemical spinodal curves, and it may transform into two-phase equilibrium structure by nucleation network transformation. Schematics composition profiles at increasing times in an alloy that is outside the spinodal domain. Here x1 and x2 are the compositions of the product phases, and x0 prime is the average composition of the alpha phase, and the composition is considered as uniform throughout. So what will happen if nucleation is occurring is, here the composition of the nuclei will be substantially different from the either of the. So here what you see here is x2 is nucleating from x0 from a phase which has got a composition x0 prime, and x2 is much richer in the beta than the average composition, and for this to happen, the B atoms have to diffuse from outside the growing phase particle to the phase particle. As a consequence, the thickness or the volume fraction of the x2 phase will increase. Sorry, A2 phase will increase, which has got a composition x2. So the diffusion is taking place down the concentration gradient here. So this is what is known as the normal diffusion. So the growth progresses by continuous pumping of the atoms surrounding these growing particles from the matrix. So B atoms are moving, and so consequently the growth of this particular phase increases by sideways advancement or linear growth. So consequently you can see here the concentration in this particular region is decreasing. So this is a different phase, this is a nuclear, this is a depleted matrix phase. So the matrix is progressively becoming depleted, and ultimately it may reach a condition where the composition of this is same as that of the x1. So this is the situation. So you have got a phase which is rich in the b given by x2, and you have got a phase which is linear in b given by x1. So but what is happening here is the nucleation is occurring and the diffusion is occurring down the concentration gradient. Now let us talk about the spinodal decomposition proper. The spinodal decomposition is a transformation that does not have any thermodynamic barrier. Thus there is no barrier to nucleation either. In it, a single phase of two or more components decomposes into two or more phases of distinctly different chemical properties. Since there is no thermodynamic barrier, the transformation proceeds by uphill diffusion. Spinodal decomposition produces a very finely dispersed microstructure, and such microstructured materials may have enhanced mechanical and physical properties. Also, spinodal decomposition is observed in several binary alloys. Examples are aluminum, copper, aluminum, zinc, aluminum, lithium, iron, molybdenum, iron, aluminum, iron, chromium, gold, nickel, bismuth, zinc, aluminum, zinc, copper, cobalt, nickel, aluminum, nickel, chromium, nickel, moly, nickel, vanadium, nickel, silicon, and tertiaries such as aluminum, nickel, cobalt, and then copper, nickel, iron, and iron, nickel, aluminum, and then iron, nickel, copper, then quaternary alloy, iron, aluminum, chromium, nickel, and many others. Gradient energy of a diffusing interface. The phases formed in spinodal decomposition are mutually coherent. There will be an additional energy associated with the coherence that exists between the product phases. While initially the interface is diffuse, but as decomposition proceeds, the concentration differences become more sharp. So interface becomes less diffuse. Because the magnitude of coherent interface energy depends on the composition gradient across the interface, it is called as a gradient energy. The origin of gradient energy is the increased number of like nearest neighbors in a solution containing AA, BB, and AB type of bonds. Negative quotient of diffusion. The flux of diffusing species is proportional to the chemical potential gradient. So this is expressed as the flux J is equal to minus M. M is the mobility, diffusion mobility, multiplied by dou mu dou x, where the dou mu dou x is the chemical potential gradient. The chemical potential mu is a chemical potential, and it is defined as dou J dou capital X. So we can write J is equal to minus M dou mu dou x is equal to minus M dou mu dou capital X multiplied by dou capital X by dou small x. So this is equal to, so by inserting mu is equal to dou J dou capital X, so this results in J being equal to minus M multiplied by partial derivative of dou J dou capital X with respect to X, capital X, and multiplied by dou capital X dou small x. So this again is equal to minus M dou to G dou x2 multiplied by dou x small partial derivative of dou capital X with respect to small x. Compared with a fixed, comparing with a fixed first law of diffusion, J is equal to minus D into dou capital X dou small x. We have the diffusion coefficient is equal to m times dou 2G dou capital X2. Here the mobility of atoms is always a positive quantity, so they are, in the sense it can be 0 or greater than 0. The sign of D depends on the sign of dou 2G dou X2. When the latter is negative, the diffusion coefficient will be negative, that is uphill diffusion will take place. Inside the spinodal region, the decomposition proceeds with uphill diffusion. Thus, component A diffuses from a spatial region of low A concentration towards a region of high concentration of A. Component B diffuses from a spatial region of low B concentration towards a region of high B concentration. Schematic composition profiles at increasing times in an alloy quenched into the spinodal region, and this alloy has got a initial average composition of X0, and X1 and X2 are the compositions of the two phases which can exist thermodynamically in equilibrium in the spinodal domain. So initially at time t is equal to 0, the composition is uniform with respect to distance, and then as time increases, the compositional fluctuations are amplified by what is known as uphill diffusion, and so consequently the amplitude of variation goes on increasing, and you have the profile which is shown here. So there are some regions where the concentration of B is depleting, and then there are regions where in the neighborhood there are regions where the composition of B is enhancing. So consequently B atoms are being shifted from this part of the phase into this part. So this is what is called as the uphill diffusion. Ultimately, when time increases, these solute depleted regions will attain a composition which is X1, and solute enriched regions will attain a composition X2. So consequently you have got a structure which is interpenetrated network of two solids X1 having composition X1 and X2. Figure shows schematically the evolution of compositional fluctuations with time during a continuous transformation. Salt solution phase alpha with a homogeneous composition X0 exists at a temperature T1. When quenched to T2, it becomes unstable. In continuous transformation process, the composition fluctuations are amplified with time until a two-phase equilibrium structure containing alpha 1 and alpha 2 is evolved. The composition fluctuations evolve with the time. They are solutions of fixed second law of diffusion, which is dou capital X with dou T is equal to m, that is the over NV multiplied by dou 2G dou X2 multiplied by dou 2 capital X dou small x2. So which can be again written as m over NV, and then G double prime, that is a second derivative of G with respect to the composition variable capital X, multiplied by dou to capital X and dou x2, with respect to the partial derivation with respect to small x, spatial variable. Here NV is the number of atoms per unit volume. This equation is valid when the driving force for transformation is the chemical potential gradient. However, when the fluctuations are formed, two more energy contributions are ought to be taken into account. These are, the first one is interfacial energy of a diffuse interface created between two phases. So this energy term is also called gradient energy, can be taken into account by writing G as the volume integral of G capital X0, that is the base, the free energy of the base composition, or the parent phase composition, plus K again multiplied by dx, d capital X dx squared. So then the modified chemical potential in this case is mu is equal to dou G dou X minus 2K dou 2X dou capital X dou 2 capital X divided by dou X dou small x2. The second component which ought to be considered is what is known as strain energy due to coherence between two growing phases, alpha 1 and alpha 2. This contribution is significant during the early stages of spinodal decomposition. This energy is eta times y into x minus x0. X minus x0 is the amplitude, where eta is equal to 1 over a into dA d capital X. So A is the lattice parameter and Y is elastic modulus, which is given by the tensile modulus E over 1 minus mu. When these two energy factors are considered, the modified diffusion equation is dou capital X dot is equal to m over nV multiplied by G double prime plus 2 eta square y, and again this is multiplied by dou to capital X dou small x2 minus 2k dou 4 capital X dou small x 4. The entire diffusion coefficient is given by d circumflex, so which is here is we can represent it as equal to m diffusion mobility multiplied by the G double prime over nV, and then introducing it we can simplify it as dou x dou t is dou capital X dou t is equal to d prime and multiply by a term which consists of 1 plus 2 eta square y by G double prime multiplied by dou to capital X dou x2 minus d flex 2k G double prime multiplied by dou 4 capital X and with respect to dou small x 4. This is the differential equation for diffusion in spinodal decomposition. The solution of it is of the form capital X minus x0. So x0 is the composition of the parent phase. X is the current local concentration. This is equal to a function A, which is a function of beta and t, multiplied by a cosine function of beta multiplied by x. So this can be further written as A function of beta and 0 multiplied by exponential r beta multiplied by t. And this and then further the cosine beta x. In this equation, r beta is called as the amplification factor. Concentration of wave amplitude increases exponentially with respect to time. Beta is equal to 2 pi by lambda is the wave number. The lambda is the wavelength of concentration profile. So the amplification factor r beta is plotted as a function of wavelength lambda. So you have got two terms here. One is a positive term which has got beta square time, and then you have got a fourth order time which is negative. So as a consequence of balancing of this, you have got a curve which initially increases is positive, and then subsequently beyond a critical value of beta the curve becomes negative. So in the positive quadrant this curve has got a beta maximum value. So for a given composition and a temperature, inside a spinodal domain there is a critical wavelength lambda c. Only those concentration profiles with lambda greater than lambda c have amplitude amplification factors greater than 0. Likewise, there is a maximum of wavelength lambda max which dominates the final microstructure consisting of phases alpha 1 and alpha 2. The comparison between spinodal decomposition and nucleation growth. An initially homogeneous solution develops fluctuations of chemical composition when supercooled into the spinodal region. These fluctuations are at first small in amplitude but grow with time until there are identifiable precipitates of equilibrium composition. In contrast, during nucleation and growth, there is a sharp interface between the parent and the product crystals. Furthermore, the precipitate at all stages of its existence has the required equilibrium composition. Spinodal decomposition was uphill diffusion, whereas diffusion is always down a concentration gradient for nucleation and growth type of transformations. So here is a table comparing the nucleation and growth type of transformation with the characteristics of spinodal decomposition. Free energy versus composition curve in the case of nucleation and growth growth type of transformation has got d to g dx2 greater than 0, and it is so that is the curvature of the Gibbs free energy with the composition is positive here for nucleation and growth. So for spinodal decomposition, the curvature is negative, that is d to g d capital X2 is less than 0. Under what conditions the nucleation, the transformation occurs? So, nucleation, the growth type of transformation, occurs when the alloy is cooled below a critical temperature. In the case of spinodal decomposition, so you require a composition fluctuation which will be amplified. So in the case of nucleation, the growth type of transformations, nuclei are formed and they grow. So in the case of spinodal decomposition, nuclei they do not form. Composition change from a matrix to new phase is very large in the case of nucleation and growth type of transformations. It is essentially there is no change or a small change in the case of spinodal decompositions. Structure change from matrix to new phase. It is typically large in the case of nucleation and growth type of transformations, and in the case of spinodal decomposition there is no change. The interface is distinct and sharp in the case of nucleation and growth type of transformation, and in spinodal decomposition the interface is diffuse but not well defined. Direction of diffusion is downhill in the case of nucleation and growth type of transformation, whereas in the case of spinodal decomposition it is uphill. Rate of transformation is slow in nucleation type growth kinetics, and it is fast in spinodal decompositions. Precipitate size and distribution is in the case of nucleation and growth type of transformations, small number of precipitates with large size are formed. In the case of spinodal decomposition, large number of precipitates with small size are formed. So the structure is highly disseminated. Nucleation growth process essentially involves formation of a stable nuclei of critical size and the growth of the nuclei of size greater than the critical size. In the case of spinodal decomposition, there is no thermodynamic barrier, and domains are formed as a consequence of spinodal decomposition. So again, the transformation kinetics, the transformation itself is explained by means of what is known as Ostwald ripening. So, and in the case of spinodal decomposition, the phenomena is explained by Cahn-Hilliard approximation. So this is typically a numerical simulation showing the kinetics of spinodal decomposition. The system is initially near an unstable concentration in air, and initially decomposes into two distinct phases with composition XA shown as black and XB shown as white with a characteristic length scale C and D. This is shown, you can see the length scale is increasing with the increasing time. So the evolution and coercing of the length scale can be seen while maintaining fixed phase fractions. The effective time interval between the images increases from, in this situation, from A to F. So this is again a sequence of stages in which samarium, cobalt, copper intermetallic undergoing spinodal decomposition. So the progress is tracked with respect to time. So the entire transformation is over within of that of 30 seconds.